All right, so what you've got down so far is I know how to find an equation of a line. Y minus y1 equals m times x minus x1. Whatever the line is, I know how to find an equation. To find that equation, I need a point and a slope. Well, point's pretty easy, generally given that, or at least given an x value, and you can find the y value to go with it. Or in the slope, sometimes there's more work. You're going to get that derivative and that value. The other piece that you know, the derivative represents the slope of any tangent line. Any tangent line. So if the derivative is 5x, then that is the slope of any tangent line along the curve would be 5x. If I want a specific tangent line or at a specific point, then I have to substitute that x value in. Okay with that? All right, now, one question came up, well, do we not use the y? All right, well, the reason we're not using the y value is because there's no y's in the derivative. If the derivative is 5x plus 1, the derivative is 2x squared minus 7. They're just x's. That's why it's just the x value. In the future, we will see derivatives that have both x's and y's in it. So then you would have to substitute the ordered pair, the x and the y value. It's just right now, the only derivative value or derivative variable in there is x. So that's why we're just using that. Does that make sense to everyone? Okay. Now, the derivative is the slope of the tangent line. So what we're going to look at, and this is in section 2.2, we're going to look at some basic derivative stuff. Now we're not going to, these derivative rules. It's not every single derivative rule out there. We're just going to talk about some basic ones. Now let's look at some graphs first. Pretty basic sketch there. Basic parabola. Now we talked about last time things like increasing, decreasing, slope to tangent line, stuff like that. So this graph is decreasing. It gets to right here and it starts increasing. Everyone agree with that? So are the slopes of the tangent line positive or negative over here? Negative. You just kind of visualize them being drawn anywhere. They're negative. Now it's more negative here than here, right? That's for sure. Okay. And then the slopes of the tangent line turn positive. A little bit positive, more positive. As we're moving along, it gets more and more positive. Does that make sense to everyone? Okay. What's the slope of the tangent line right here? 0, because it's not increasing or decreasing. We can actually draw the derivative. I'm going to first find my 0. Put it there. It looks a little off-center to me. We're just getting an estimate here. Okay. So that's where the derivative 0 matches up with that min. You said it's really negative to less and less negative approaching 0. Really negative to less and less negative approaching 0. Then it turns a little positive, but then gets more and more positive. There's f prime of x. Now, is that the exact f prime? Probably not. I'm just kind of guesstimating based on the sketch I have. All right, so again, review. It's 0 here. 0. It's negative back here. Look back here, it's negative. A little bit negative, a lot negative. Turns a little bit positive, gets a lot more positive. Okay there? Different sketch. So we're just got a basic function there. We're going to go find the derivative now, or sketch the derivative. Right. How many places on that graph is the derivative 0?
3. On that graph.
2. 2. Okay there? You see a max, a relative max, and a relative min. So 0 here, and about right here. Everybody agree with that? So let's think here. We're increasing. Positive slope, 0 slope, negative slope, 0 slope, positive slope. Does that sound right? Okay. I'm going to put a 0 there. Your sketch that you did on your paper might be a little off from mine, but you can still tell what the zeros are. Okay. Positive slope, really positive, getting closer to 0 positive. Everybody agree? Really positive, getting closer to 0 positive. Then I turn a little bit negative. Then I get more negative. Then I get less negative, back to 0. So again, visualize a tangent line on here. The reason I curve back, okay, that's a negative slope. That's a negative slope, but that's a lot more negative. Does that make sense? Okay. So I got a little bit negative. Let's put numbers in here. Negative half to negative 4 to negative half. That make sense? Like that? All right. Let's see. Then we get back positive. Past 0. A little positive. More and more positive. What are we doing there? We okay? Okay. Go on. Okay, you draw the rough sketch of what you think that derivative looks like. Do what I did in the last two. Find the zeros first. And you should have 3 zeros. Give it a try. Don't worry about being right or wrong. If you need to redraw it correctly in a minute, redraw it. It's not a big deal. Let's take a look at what you've got. You got a 0, 0, 0, roughly in 3 spots. Positive to 0. Negative back to 0. Positive back to 0. And then negative. Now look at the generalized shape, okay? Don't worry about if you made this more shallow or deeper. I'm not worried about that. Just the generalized shape's what we're worried about here. Okay? I can't get really exact as far as how steep to go or anything without some numbers in there anyway. You just want that general shape. How'd we do there? We do okay?
Yeah.
Have you noticed anything?
It kind of.
The derivative is always 1 degree lower.
Drops 1 power, right? Think back to your homework. You worked that whole derivative process and it dropped a power. Make sense to everyone? All right. So if it's a polynomial, we have what we call a power rule for our derivatives. So, power rule. If f of x equals x to the n, f prime of x equals n x to the n minus 1. Power comes down, new exponent is 1 less. Okay, so again, let's look at our graphs. Now, I don't know what any of the equations are, but I know the original was a quadratic, it's x squared of some sort, drops to a linear, just an x. Here's a cubic, x cubed, drops to an x squared. Here's a 4th degree, drops to a cubic. And you may remember something like this had to be a negative 4th degree because they're both down, and this is a negative cubic because it's flipped upside down. But either way, you can see the power drop. Okay there? Okay, here's the one that was asked on the homework. Well, that was referred to as far as the tangent line. What do you got?
So is that why the one that was just the square root of x, is that why that one became just 0? Because it was already at just 1 power, so it dropped to 0.
No, if it's a square root, it's a half power.
Oh,
So then if it drops 1, it goes to negative half.
okay, so I did that wrong.
All right, we'll look back at that one. All right. So here's the one that was asked on, I think it was 27 or something. And I said, well, did you get 3x squared for the derivative? And he said, yeah, I did. So we didn't go through the limit process, but let's look at it. Power comes down. Power minus 1. My derivative.
Oh my gosh. I feel so.
Power comes down, power minus 1. Now, that doesn't mean that you don't have to know the limit process. Okay? The reason we discuss the limit process is because we have to understand that it is still a slope. Everybody agree it's still a slope? Okay. How many points do you need to find a slope? 2. Well, if I'm trying to find a slope at 1 point, I run into a problem because I need another point. So we're trying to get infinitely close. There was that delta x goes to 0 idea we talked about. That's going to come back again and again and again. Those limits aren't going anywhere. Right? When it's a polynomial or other types, we have certain rules that we can use. In this case, any of these are polynomials, they will drop 1 power. So let's kind of mix some others in here, and then we'll look at a couple other graphs in a minute. Let's get some others. If f of x equals 3x squared minus 5x plus 1. Go back here, I'll call that number 1, we'll say number 2 here. Then f prime of x. Now this is 3 terms, but we just do 1 term at a time. 2 comes down. 2 times 3 is 6. X minus 1, that would be just the first power. Minus. Power's 1 up here, right? 1 times 5 is 5. And technically this would be x to the 0. Would you agree with that?
Yeah.
But x to the 0 is 1, right? So I really don't need to write it. Okay? I just want you to understand it's really not disappearing. It just has 0 power. Okay? And then that disappears. Now this is why it disappears. Wouldn't that really be x to the 0? Would you agree with that? Okay. 0 comes down. What's 0 times 1?
0.
So it just zeroes out the term. So the derivative of a constant is 0 simply because, well, it's still that same power rule. It dropped 1. Okay, that 0 is coming down. Okay? Because there really is an x term there. We never write it, but we do realize there is an x to the 0 there. Are you okay with that?
Yeah.
All right. Let's say f of x equals 4x cubed plus 3x squared plus 2x minus 5. F prime of x. So this was our notation we got introduced to last time, that prime. So what would 4x cubed become?
12x squared.
12x squared. This is at least faster than the limit process, right?
Yeah,
Oh, yeah.
for
Okay.
sure.
Says us.
How about 3x squared?
6x.
6x. How about 2x? How about negative 5?
Cancel.
0 or cancels out. That's my derivative.
Oh my gosh.
Are you okay there?
Yeah.
Okay. Here's a new notation. We're going to see some various notations, so I try to just kind of slide them in every now and then. So originally, the way I gave it to you in a notation was I gave you f of x, or it could have been g of x or anything. Doesn't matter what letters there. Then I said find f prime, or that first derivative. This says find the derivative with respect to x of this. So that means this inside is that f of x. This is just all in one telling you find the derivative of that. Why is there an x? Because there's an x in there. No tricks there. Okay. So this would then be 6x plus 5. Same power rule, nothing changed. Different notation. So this variable is representing what's in here. Just like when you're in your function notation, this variable is representing the variable that's in there. So that being said, if I said derivative with respect to w, what variable do you expect to be on the inside? W. All right, so here we go. 5w squared plus 1. It doesn't matter what variable's there. We got to get comfortable seeing different variables. Yes, we're generally going to see x's and y's most of the time. Okay, but we have other letters out there. So this would be 10w.
Yes.
So look, everybody good there? All right. Derivative with respect to y.
Wait, sorry, I was writing some down. So with the number 5, with the 1, how come the 1 becomes just the 0? Okay.
What's the power of the w that's on the 1?
0.
0 comes down. 0 times
Oh.
1.
Right, I was thinking about times negative. Okay, yeah.
All right.
Oh, sorry.
All right, let's go with y to the 1/2. Don't change your rule. Where is that 1/2 going to go? Down. You get something you don't like, that doesn't mean change the rule. Okay? So now what's 1/2 minus 1? Are you okay there?
Yeah.
Now some different ways of looking at this. This is correct. Nothing wrong with this. You could also write that as 1 over 2y to the positive 1/2. Remember how you can remove negative exponents, moving them up and down. You could even write this as 1 over 2 square root y. Because the 1/2 power is a square root. I want you to understand that any of these are correct. One of the things that you've got to get used to is you're going to see various forms of a solution. So for me, all right, and in Calc, you don't have to simplify anything. So for example, if I got this for an answer, okay, and I'm taking a test, that's what I've got. Hey, that's right. Okay. I'm on my homework and I get this for an answer, and I look in the back of the book and see this one with the square root in there. I need to mentally understand that these two are the same to know I'm right. Does that make sense? So as we move further, we're going to get to some things that we still don't have to simplify, but we may need to make sure we're getting the correct answer. So we're going to see some different forms. You're taking a test. This is what you get. It's multiple choice question. That's not any of the choices, but this one is. You got to realize that's the same answer. Mark that choice. I mean, you would not have this is A, this is B, this is C. That's not a fair question.
Unless D's all of the above.
So just kind of keep that in mind. We don't have to simplify everything, but we do need to realize there's different forms that are going to come up. Something like that. Okay? So that being said, I gave it to you like that. So let's go 7. All right. Here we go. F of x is cube root x. All right, so this time I give it in a radical formation. All right. We don't have a radical rule. We have a power rule. So that doesn't do me any good. I need an exponent. Okay, what would the cube root be as an exponent? 1/3. So the first thing I want to do is rewrite that as 1/3. Now I can follow my power rule. Now you should remember back when you did some different radical things, square roots, cube roots, fourth roots. You could do some things with them, but you couldn't compare them unless you had exponents, because then you could kind of put things together. Okay, we need that exponent piece. Now we're in another situation of there's nothing wrong with the cube root of x, but that makes it tougher to operate the derivative. I need to understand that's a 1/3 power. So now f prime of x. 1/3 comes down. X. Now what's 1/3 minus 1? Negative 2/3. That's correct. You could drop the x to the bottom and have a positive 2/3. If you put it back in a radical form, that would be cube root x squared down there. Do you have to put it back in a radical form?
No.
No, but you do have to understand that these two are correct. And that's something that we're going to see some problems might take us a little bit to get used to. That I do think. We'll get used to it. Have some different forms. Are you okay there? Okay. Derivative with respect to x of 3 over x to the 5th. Well, the only rule right now that I have at my disposal is a power rule. Here's my power rule. You don't see any division in that power rule. So I need to move that 5 up. There we go. So I'm going to rewrite this as the derivative with respect to x, 3x to the negative 5. So this would be why back in algebra you did that grunt work of moving things around sometimes, because sometimes we need them in a different place to work with them. And this will be one of those examples. I need it up in that negative formation so that I can work my power rule. That's the idea. Now here comes the derivative. Negative 5 comes down. So it'd be negative 15 x -6. -5 minus 1. Does that look okay? Okay. Do you have to take the 6 or x to the 6 back to the bottom? No, can you? Yeah. Okay. And I will tell you on this particular textbook that we're using, a lot of the answers in the answer key in the back generally go back to positives. So a lot of times you most likely would see that going back to the bottom, but we just need to understand that the same. Are you okay there? All right. Let's see, 9. F of x equals pi cubed. Find f prime of x. What do you think the answer is?
No,
I heard 2 different things. I heard 0 and I heard 3 pi squared.
I don't think there is one.
Is there a variable in that problem?
No.
No. Trick question there for you.
Wait, so which be 0?
0. That's a constant. Pi is a number, right?
Yeah.
Yeah.
All right, so that's the derivative. So there's really, technically, I guess it's this.
Yeah.
0 comes down. 0 times pi cubed is 0. Are you okay with that?
Yeah.
Little trick because you see the power. The key is to make sure that you're focusing on, hey, I need to know what my variable is I'm working with, okay? Everybody all right with that? Okay, let's look back at a graph again. Here comes another graph. Pretend it's a nice, perfect looking graph. If I remember what that graph represents, it's a sine. Okay? So I'm just going to write out here to the side f of x equals sine x as a basic sine curve. Right, now let's graph the derivative. How many places on that sine curve is it 0? 2. All right, so we're going to have 1 here. And 1 about there. Everybody agree?
Yes.
Okay, so we're going to be positive. Hit that point. Come negative. Curve back to that point. And positive. Does that sound familiar based on what we were doing?
Yeah.
All right. So here is my sketch.
Whoa, that's sick.
What graph does a sketch look like?
Cosine.
Cosine. So f prime of x is cosine x. You there? Let's look at another graph. This time I'm going to draw a basic cosine graph. And again, even if you're not the most familiar with, say, sine and cosine, you know what the basic sketch kind of looks like. You may not remember every little point on the graph. You kind of have a visual of what the basic sketch is. So this should be 0. Oh, here we go. I didn't write it up there. F of x is cosine x. Get that on there. This would be 0. And at the end, it'd be 0 because you know on each side of the cosine, it's going to curve down and start another period. Okay. So we are negative back to 0. Then we are positive back to 0. What does that shape look like?
Sine.
Oh, you're close. It's not
Negative
exactly
sign.
sine. Negative signs. It's flipped upside down, right? You definitely see a sine shape, but it's flipped over. So here, f prime of x is negative sine x. So you have 3 rules to make sure that you have memorized going in the next class. One's a power rule. Power moves down. That's not too bad. Well, your second one would be the derivative with respect to x of sine x is cosine x. And the third one, derivative with respect to x of cosine x is negative sine x. There's our other 2. Now we'll use those 2 trig functions to get the other 4, because you should remember there's 6 trig functions. Okay. Now we did the sketches there proving as far as what the derivatives were, so you can kind of see where they came from. Now let's mix the 2 together. Let's say f of x equals 4x cubed plus sine x minus square root x. Just trying to mix some different things in. You have 3 terms there, which means we're going to take the derivative. We're going to deal with the 4x cubed first. We finish that. We'll go deal with the sine x. We finish that. We'll go deal with the square root x. One at a time. So f prime of x, 12x squared. Everybody agree with that? Okay. Plus sine, the derivative of sine is cosine x. That was our derivative of sine. Minus, now remember, we're not supposed to think of that as square root x. Remember, we think of it as, sometimes it's nice to write it out to the side. I'm thinking of that as x to the 1/2. I need that power. So then that would give me 1/2 x negative 1/2. Everybody okay there? All right. How about the derivative with respect to x of 3 cosine x minus 2 sine x plus 5. Now I'm taking the derivative with respect to x, so on that first term, the cosine x is what I'm worried about. I don't care about the 3. I mean, the 3 is not going anywhere, but that's just a coefficient. So what was the derivative of just a plain cosine x? Negative sine x. So that means this would be negative 3 sine x. 3 coefficient is still just sitting there. And then the derivative of just a regular sine x would be cosine x. So this would be minus 2 cosine x minus, because it was already minus. Nothing changed there. And what's the derivative of 5?
0.
0, doesn't matter. Are you okay there? Okay. If I gave you this look, derivative of 3x minus 5 times 2x plus 1. The 3 rules that you are supposed to get down are a power rule, the sine, and the cosine. That's a product. That's not a power rule. It's definitely not a sine or a cosine. Everybody agree? So even in a situation like this, sometimes we need to actually rewrite it. 6x squared minus 7x minus 5. I need to know what I'm working with. We can multiply it out. Now I'm back to that polynomial. F prime of x, 12x minus 7. Everybody okay there? All right. So sometimes you got to do some rearranging just like you would on a radical function. All right, that being said, circle back to that limit idea. And you don't need to write this down, but let's take a look at a parabola. Okay, zero slope here. Really positive, less positive, little negative, more negative. All agree? Okay. Versus an absolute value. This on a parabola, really positive, getting closer and closer to zero. Everybody agree? That's a constant. That's not changing. That's not changing slopes getting closer to zero. It's staying whatever that positive value is. Everybody agree with that? That's staying whatever negative value is. They are not approaching zero. Everyone agree with that?
Yeah.
So let's say this like a 2, slope of 2. Well, it's 2 everywhere, right? Let's say this is -2. It's -2 everywhere. That means the derivative does not exist right here. I'll put this on a regular graph for you. Here's an absolute value. You've seen that before, just a V shape. Okay. Is this slope over here positive or negative? Negative. Does it change? No. So it is a negative constant. This slope over here is a positive and it doesn't change. Positive constant. So the dotted line is still the derivative, solid the original. Constant to constant. Now I don't know how constant because I don't have any numbers up there. Okay. I know this is a constant negative, but without some actual values, I can't tell you if it's -3 or -2, but I know it's a constant negative. Again, we're just trying to get a generalized sketch. Okay with that?
Wait, so there is a derivative?
There is a derivative, not at zero.
Oh, okay.
So there's a derivative back here, derivative here, but not at zero because it didn't approach zero. Remember our limit function, it has to approach the same from both sides. This guy's approaching zero from both sides when you think of the slopes. That's a constant to a constant. It's not approaching zero. It stays constant. There's the idea of why we still have to understand the limit concept. Okay, your homework going to be working with the rules. Let's get your homework.